Alright, so picking up right where we left off here, this is the Lecture 9B chunk. We are going to pick up right where we left off and truly get into redox reactions themselves now. We've set things up quite nicely, I think. Of course, we started off with the terminology definition of standard states, just so we had that under our belt, and spend the rest of our time in the first chunk of this lecture series discussing metabolism in general, and ending with the idea that catabolism is more of an oxidation process, where we steal energy from the food we eat by stealing electrons from that food, and that anabolism is more of a reductive process, where the way that we put energy into these systems to build new molecules is by putting electrons into them, because the electrons hold the energy. So we're in a good place now to talk about the role of redox reactions themselves, what redox reactions are, how they work, and then we will move on in the last chunk to the role of coenzymes in redox reactions, this idea of enzymatic coupling to achieve a favorable overall reaction, even when we have to drive reactions forward that have positive delta Gs, and this idea of activating non-reactive molecules, and coenzyme A will be our example there. So as I said, let's just dive right in and talk about redox reactions themselves. I've already kind of given the beginning of this in the last chunk. When we say we're doing redox reactions, we're really doing electron movement reactions. Redox reactions are the transfer of electrons from a donor to an acceptor. Whenever a molecule loses electrons, whenever a molecule has donated electrons to some other system, we say that that molecule has been oxidized. So oxidized molecules have lost electrons. And likewise, when a molecule gains electrons or accepts electrons from a donor, that molecule that is gaining electrons is said to be reduced. Now, there's two ways you can remember this. The way that I remember it is I always tell myself it's counterintuitive. If you've told me I'm reduced, I think I've lost something. Reduced means less, right? So I always think that makes no sense at all, because in this case, I gained electrons, yet you're calling me reduced. And so I always remember the fact that it really doesn't jive, that in this case, something that is reduced is actually something that gained electrons. The reason why reduced is used is because of the charge perspective, so you can also remember it that way. Imagine that you have a charge of positive 2. You're an ion, a cation with a positive 2 charge. And now imagine that you gained an electron. Well, what would happen if you gained an electron? Your charge would now be positive 1 because the electron was negatively charged. In other words, your overall charge was reduced. And so that's the real reason why that word is used. So no matter how you remember it, always remember that a reduction reaction is the gain of electrons, that molecules that are reduced have gained electrons. And if you can remember that, then the oxidation takes care of itself, because it's the opposite state, it's the donating of electrons. A little bit more terminology. So if I am a compound and I caused you to gain electrons, if I caused you to be reduced, I am then a reducing agent because I made that happen. So you can think of beta-mercaptan ethanol as an example of this. Many of you have probably used BME in a lab. It smells like rotten eggs. It's pretty nasty stuff. What BME does is it reduces disulfide bridges. It breaks disulfide bridges between cysteine residues, and it breaks them by adding electrons to them. It breaks them by reducing them. And so this is the oxidized form of a disulfide bridge, and this is the reduced form, and you can see that this reduction has broken the disulfide bridge. That makes BME a reducing agent because it caused this disulfide bridge, it caused these two cysteines to become reduced. There are also oxidizing agents, which at this point probably you understand that they cause other things to become oxidized. So we'll be dealing with reducing and oxidizing agents quite a bit as we go through metabolism, because every time we need something to lose electrons, we need an oxidizing agent. We need something to force that to happen. And likewise, whenever we need a molecule to gain electrons, we're going to have to require the help of a reducing agent. So let's take the simplest example of a redox reaction that we can think of. This is a non-organic, inorganic redox reaction. It has nothing to do with metabolism at all, but it's the simplest case, so it allows us to kind of track the movement of electrons in a very intuitive way. So this example, this thought experiment, is going to involve us taking a small zinc bar, solid zinc metal, and putting it into a solution that has dissolved copper ions. So that would look like this if you were to do it. You can see the water is bluish in its tint. That is because copper is dissolved in the water. Copper metal, copper ions are dissolved in the water. and there's the zinc bar, silver-looking bar in the center of that beaker. So why are we doing this? Just trust me, let's do it. We put a zinc bar in a solution of copper. After a little while, something pretty magical happens. The zinc appears to disappear, and instead, copper metal has deposited on that zinc bar. In other words, copper metal has gone from being aqueous in solution to being solid, falling out of solution. And this is what you would see after a little while. You would see that that bar is now brown in color, it's plated in copper, and you probably see, especially if you got a nice screen in front of you, that the water is no longer quite bluish in its tint, but it's a little bit more green or turquoise. So the color of the water has changed. So the question is, what happened? What just happened before our eyes? And the answer is this happened. This chemical reaction captures what occurred in that beaker. Essentially, ionic copper, aqueous copper, copper in its +2 state, therefore it was able to interact favorably with water, interacted with the solid zinc metal, which was neutral in charge because it was in its solid state, and the copper shifted to being solid itself, no longer ionic, and the zinc instead became ionic and therefore went into solution. So where we had copper in solution and zinc as a solid to begin with, we now have copper as a solid and zinc in solution as the reaction ends. Well, the next question is, okay, that's great, but what really happened? What made that occur? And the answer there is that electrons were transferred. In this case, the zinc metal lost 2 electrons. Zinc starts off as electrically neutral. If it loses 1 negative electron, its charge will go to +1. The charge of zinc will go to +1. If it loses 2 electrons, its charge will go to +2. In other words, if you take zinc +2 and add 2 negatively charged electrons, you would go to zinc 0. We're saying this happened the other way. Zinc electrically neutral at 0 lost 2 electrons and has gone to zinc +2. So zinc lost those 2 electrons. Once it was in its +2 state, it could interact with water, and it dissolved in water, hence the zinc being in solution. Well, let's go back to our terminology. If we're saying that zinc lost 2 electrons, anything that loses electrons was oxidized, so zinc was oxidized. And the question becomes, what happened to copper? Well, the 2 electrons that zinc lost were absorbed by copper. Copper has a +1 charge. Copper here has a +2 charge. So when that copper accepts the first of zinc's electrons, its charge goes from +2 to +1. As copper accepts the second of zinc's electrons, its charge goes from +1 to 0. Once copper is at an electrical charge of 0, it can no longer interact with water, it precipitates out of solution, and plates the metal bar. We're saying that copper received and accepted 2 electrons, and anything that receives electrons was reduced, so the copper in this case was reduced. So what we're looking at here on the right in this reaction is a redox reaction. It is a reaction of the movement of electrons. Electrons went from zinc to copper. Zinc was oxidized and copper was reduced. But oftentimes, to kind of clarify things, we will represent redox reactions as half reactions. We will separate the reduction and oxidation reactions from one another. So for example, the half reaction of reduction here would focus exclusively on copper. Copper, in its aqueous form with a +2 charge, accepts 2 free-floating electrons, and when they merge together, copper goes from +2 to neutral. We can also represent the half reaction of oxidation. For the oxidation, zinc started off as a neutral solid, had no charge, but as it lost 2 electrons to the environment, its charge became +2. The other thing that you can see in this diagram of these half reactions is that the electrons are always on opposite sides of the arrow. For the reduction, the electrons are on the left, and for the oxidation, the electrons are on the right. And that makes sense because the electrons should essentially cancel each other out when we combine those half reactions. If one thing lost electrons and the other thing gained them, then the electrons themselves are no longer free-floating. If we go back to this idea of agents, we can also see that if zinc caused copper to be reduced, zinc was the reducing agent. Zinc forced its electrons upon copper. And so zinc is the reason why copper was reduced. Zinc is the reducing agent. Likewise, copper is what stole zinc's electrons. Copper caused zinc to be oxidized. So copper, in this reaction, can be thought of as the oxidizing agent. Again, this is the simplest redox reaction we can show. It beautifully shows the transfer of electrons not only schematically, but in a way that we can see with our naked eye, as I showed you with those metal bars in the beaker. And it gets at all of the main concepts we're after in terms of oxidations, reductions, movement of electrons, half reactions, and agents. I will tell you that this reaction is far simpler than anything we will see in biochemistry. It's far simpler than anything that occurs in metabolism, but it's a nice entry point for redox reactions in general. So it's a good way to understand everything that happens as electrons move from donors to acceptors in redox reactions. So let's bridge now to the role of coenzymes in redox reactions. I imagine that you've encountered redox reactions before. I don't think anything I just told you is all that new. So hopefully this was just review. But the redox reactions we will see in metabolism are quite different from these inorganic redox reactions that you're probably more familiar with. Living things use redox reactions for the same reason that zinc and copper were, to move electrons. The reason why living systems are moving electrons with redox reactions, though, is to shuttle energy around from one molecule to another. Also, it's fair to tell you that this is not a chemistry class, so you've probably dealt quite a bit with electron reduction potentials and Faraday's constant and the Faraday equation and everything that goes with that. We'll touch on the basics of that in a few weeks, but we're certainly not going to do any of that here. We're not going to go to the numbers and the calculations. We're really just interested in redox reactions for what they are, for why they're important in biochemistry, and that is that they move electrons around. Also, whenever possible, we will try to simplify things by showing the pertinent half reactions rather than the entire reaction. And so here is a good example of a biochemical redox reaction. In fact, this is a redox reaction that we will see much later on as we talk about the metabolism of glucose. So in this reaction, we see that ethanol has been converted to acetaldehyde, and as a result, 2 electrons have been lost by ethanol and 2 protons as well. So even though it's there in the label of the half reaction, we instantly know we're looking at an oxidation reaction, because ethanol lost electrons. In order to become acetaldehyde, ethanol lost electrons, and anytime electrons are lost, we're dealing with an oxidation. In fact, we can track them. This is one of the electrons that was lost. This is the other electron that was lost. The reason why those hydrogens popped off of ethanol as a result of this oxidation is because those covalent bonds were disrupted by these electron losses. So 2 protons of hydrogen were released, and the remaining electrons, those remaining unpaired electrons that we see there on oxygen and carbon, came together to create the second bond of this double bond we see here of acetaldehyde. So all the electrons are accounted for. 2 electrons were lost, the other 2 electrons came together to form a new covalent bond, and protons were released because of the disruption of those covalent bonds. What we also see here is another useful hint that we will use again and again in our redox reactions for biochemistry. Where electrons go, protons follow. You see, unless we're looking at half reactions, we don't see the electrons of redox reactions. They're not represented in the reaction diagrams, but we will always see the protons. So we see here that when protons were lost is when the electrons were lost. So anytime we see a molecule losing protons, we will always know that that molecule was oxidized, because if protons were lost, we know electrons were lost as well. And likewise, whenever we see that a molecule has gained protons in a redox reaction, we will assume that electrons were gained as well, because wherever the protons go, the electrons follow, and anything that gains protons and gains electrons is something that was reduced. What we don't see in this half reaction of ethanol is the oxidizing agent. We don't see the thing that caused this oxidation. In other words, we don't see where those electrons went. We don't see what got reduced. Very often, what is getting reduced in reactions such as this one, what is the agent forcing these reactions to occur, are coenzymes, vitamins, You may remember we talked about cofactors very early on in the semester. In one of our early lectures, we talked about metal ions and coenzymes. I even showed you the label from some vitamin bottles, and we're back at it here. Those coenzymes are largely driving redox reactions. One of the most important coenzymes for redox reactions that we will talk about this semester is nicotinamide adenine dinucleotide, which we will, from this point moving forward, always refer to as NAD. That N of NAD, incidentally, comes from niacin. That's why niacin is an important vitamin. That's why it's in your daily multivitamin. We need niacin to make NAD, and we need NAD to drive redox reactions forward. This is what NAD looks like. It's a very complicated molecule. You can see that its backbone is that of a typical adenosine nucleotide. Here's the adenine nitrogenous base, a ribose sugar, 2 phosphates, and then another ribose stacked on top. Here is that nicotinamide group. It's a pyrimidine in nature, but it is not one of the standard pyrimidines we find in our nucleic acids. And this is the nuts and bolts of the molecule. This is where the redox reaction occurs. If we look over here, we see that a proton was gained versus here. And if a proton was gained, what else was gained? You better have said electrons. And so this is the reduced form of the molecule. Protons are here. Protons were gained, electrons were gained. Anything that gains electrons was reduced. If we shift from this form to this form, then we lost a proton. If we lost a proton, we also lost an electron. This is the oxidized form of NAD. So everything is occurring right here. When NAD is reduced, we refer to it as NADH or NADH plus H. In fact, NAD will carry 2 electrons. One proton will join the molecule, and the second proton will actually follow it around like a puppy dog. So NADH plus H is the reduced form of NAD plus, which is the oxidized form. And the gain of a proton, of course, in this case, is going to push bonds. We can see that because of this carbon here, it can only have 4 bonds. If we gain a second proton, then this double bond has to be pushed, and that's really the organic chemistry side of all of this, pushing electrons to accommodate new bonds. So if we go back to our ethanol to acetaldehyde reaction and we throw in our oxidizing agent, NAD, let's imagine that NADH was the oxidizing agent, or if it was the reducing agent perhaps. Let's go ahead and see that reaction in reverse. So let's take some NADH, mix it with acetaldehyde, and see what happens. So here's acetaldehyde, here's NADH plus H. Remember I told you we're holding on to 2 electrons, and so here are the 2 protons for that. Wherever the electrons go, the protons follow. And we see that now, if we count the protons in ethanol, we see we have 3, 4, 5, 6. Whereas in acetaldehyde, we have 4 protons. So this molecule has gained 2 protons. The 2 protons were gained by NAD. If it gained 2 protons, what else did it gain? 2 electrons. Where did those electrons come from? NADH plus H. And so in this case, acetaldehyde was reduced to ethanol, and NADH plus H was oxidized to NAD+. And we can see that here in these half reactions. We said that NADH plus H was oxidized, which means it lost electrons. And as the reaction proceeds forward, we see indeed that's the case. The electrons were lost and the protons followed. Once those electrons and protons were released, they were gobbled up by acetaldehyde. Acetaldehyde combined with those 2 electrons and those 2 protons to become ethanol. That's a reduction reaction because protons and electrons were gained. It's important to imagine if you took NADH and mixed it with ethanol, nothing would happen. Nothing would happen. Ethanol is fully saturated with all the protons and electrons it can carry. It is what we would refer to as fully reduced. There's no more room for protons and electrons on ethanol, so you can mix it with a reducing agent and nothing's going to happen. There's no more spots for electrons and protons to take. Acetaldehyde, on the other hand, did have the opportunity to accept electrons and protons, which means acetaldehyde was capable of being reduced. So if we mixed it with a reducing agent like NADH plus H, chemistry occurs and we see a redox reaction. Also, this redox reaction is a reaction. It's a reaction like any other biochemical reaction, and it's governed by the same rules and laws. And so in order for this reaction to be spontaneous and occur, it needs to have a negative delta G it needs to release free energy. And so this is an energy-releasing reaction. Is it spontaneous? Yes. By definition, it's spontaneous. The universe wants it to happen. Is it instantaneous? No. Remember, you didn't burn your eyebrows off when you dumped that sugar on a table. And nor is this going to happen instantaneously. It has to be catalyzed by an enzyme. And so this is why enzymes are required for metabolic processes to guide these reactions to occurring. So if you mix NADH plus H with acetaldehyde, they will join up in the active site of an enzyme. The enzyme will push and squeeze those reactants until they become something like a transition state, and then they will instantly collapse into product, which in this case is ethanol and NAD+. And just to kind of complete the story, NAD+, NADH plus H aren't the only coenzymes that are capable of engaging in redox reactions. Later on, much later on in the semester, we will see NADPH. NADPH is similar in structure to NADH, but it has an extra phosphate group. NADPH is primarily for anabolic reactions, for building reactions, and NADPH is a specialized coenzyme. It is perfect for carrying very high power electrons, electrons that are carrying a whole lot of energy. We also will see FAD quite a bit. That's flavin adenine dinucleotide, derived from the vitamin riboflavin, which we know is important for us as well. FAD we'll see quite a bit of. This is what FAD looks like. You'll see it has a purine group, a ribose sugar, 2 phosphates, then this ribitol group linked to, I won't even try to say what this is, but this 3 fused ring structure called iso. This is where the nuts and bolts happens for this reaction. FAD can also carry 2 electrons, just like NAD, but unlike NAD, FAD can also carry both protons. No puppy dog trailing behind. We can see that here. If we compare this form of FAD to the form over here, we see that we have gained 2 protons. In order to link those protons to this ring, we have also gained 2 electrons to allow these covalent bonds to be possible. And since this substance, or this form, has gained electrons versus this form, this is the reduced form, the electron gaining form. If we were to go from here to here, we have lost protons and electrons, and therefore the form would have been oxidized. So as we see FAD in its reduced form, we are going to write that as FADH2 to symbolize that both of those gained protons are now living on FAD, none of them trailing behind as we saw in NADH plus H. So to return to the main themes that we talked about in the first chunk, when we say we oxidize the food we eat, what we really mean is that we will rip every last high-power electron from the food we eat so that we can use those electrons to make ATP, energy that we can use to build the molecules we need to sustain life. So if we're going to be ripping all of these electrons off of our food substances that we're eating, that means we need lots and lots of things around that can accept those electrons and hold on to them for us. That's what these FAD and NADs and NADPHs are for. They are our electron shuttlers. They are our electron carriers. Eventually, as we get those electrons depleted in their energy, if we steal all of the energy from those electrons, at the end of the day, we're going to have nothing but energy-weak, energy-depleted electrons that we just don't want anymore. And so we need a place to put those electrons that have been completely depleted of their energy. The reason why you're breathing right now, the reason why you're about to inhale another breath of air, is to get oxygen. You're breathing that oxygen in as nothing more than a wastebasket for these energy-depleted electrons that you harvested from food. Oxygen is the ultimate electron acceptor. You breathe oxygen in solely as a place to put these electrons from the foods you've eaten once you've harvested all the energy from them that you can. Remember, I told you that where electrons go, protons follow. So as oxygen gains 2 electrons as the ultimate electron acceptor, it also gains 2 protons. And oxygen with 2 protons on it is water. So if you think about what you're exhaling right now, You're exhaling carbon dioxide. We will talk in depth about where that carbon dioxide came from as well. But the other thing you're exhaling is water. Think of your breath on a cold New England day. That water you're exhaling, that water vapor you're exhaling, is the oxygen you just breathed in, now carrying 2 spent electrons and 2 protons along for the ride. So this kind of symbolizes the energetics of metabolism as we will be discussing them as this course goes on. NAD arrives at a series of electron carriers carrying electrons and protons, and it offloads them. This complex 1 harvests its energy from those electrons, passes it to complex 2, which harvests even more energy from those electrons, onto complex 3, where still more energy is harvested, and finally to complex 4, where the last dregs of energy are stolen from those electrons. Once those electrons are completely energy depleted, and there's no more energy left to steal from them, they are considered low power, low energy electrons, and they are offloaded onto oxygen. Protons follow that reduction reaction, and fully reduced oxygen is water, which you exhale. Pretty amazing. So the only reason we're breathing right now, all of us, is to get in wastebaskets, to bring into our body places to put these low-energy spent electrons from the foods we've eaten. But as those electrons slowly move towards oxygen, lots and lots of things are oxidized and reduced along the way, and that really is the story of metabolism, the story of electrons being shuttled from carrier to carrier, changing hands as they go, allowing us to build the molecules we need for life. So you can think of the electron as the note, the stereotypical note that's being passed in the back room of a middle school classroom. So this process of getting energy out of food and turning that energy into ATP, using primarily redox reactions, is pretty much how we're going to spend the next roughly 2 months of this course. And it will bring us pretty much to the end of the course as well. Pretty amazing. Along the way, we're going to be telling the story of glycolysis, the citric acid cycle, and of course the exchange of electrons as we go, all to make ATP by the bucketful. But we already see some things on this diagram that we recognize. We see the reduction of NAD to NADH, our first event of electrons being stolen. We see the same thing is happening for NAD and FAD in the citric acid cycle. And we see the oxygen that we breathed in being converted to the water that we breathe out as it accepts those final low-power electrons and the protons that go with it. So we will move on to the next chunk by talking about how we force reactions that wouldn't otherwise happen to occur. That's going to be important in metabolism as well. And we talk about how we fool some molecules into being reactive even when they don't want to be. But until then, let's summarize what we talked about here. We talked about redox reactions, reactions that involve the transfer of electrons as a means by which we can transfer energy, and we used zinc and copper as our primary example. Whenever a molecule, any molecule, loses or donates electrons, we say that that molecule has been oxidized, and when another molecule has accepted or gained those electrons, that molecule has been reduced. We talked about half reactions of oxidation-reduction reactions as a mechanism for tracking those electrons, and then we moved on to the coenzymes we will encounter again and again, NAD and FAD. These are redox facilitators. So I hope this was clear. If not, certainly let me know in your reflections. We're going to be building on these concepts quite a bit. But until then, thank you for watching.